Okay, so we are continuing with the residue examples, or I should say the residue method cases. So we have already covered the simplest possible case, which is the simple pole case. Simple poles. So what was this? F of s is equal to s plus 1 divided by s plus 2, s plus 3, something like that. And I would like to find a over s plus 2, s plus 3, and I would like to find a and b, essentially. So last time we have covered this. So a is simply, you multiply both sides by s plus 2, then substitute instead of s minus 2. So I have minus 1 divided by 1. And b is equal to, you multiply both sides by s plus 3. There is a cancellation right now. So substitute s is equal to minus 2. Sorry, minus 3. You get minus 2 over here. And minus 1 over there. So we are getting this number as minus 1. And we are getting the other one as 2. Okay, let me write a little better. So this is equal to minus 1, and this is equal to 2. Okay, so let's give a double check. For example, if I equate this, what's the coefficient of s? So minus s plus 2s, I get s. Okay, so minus 3 plus 4, I get plus 1. That's one way of always check your results. Once you do these simple calculations, please verify them. Verifying takes just a second. So this is called the simple poles. Okay, so simple poles means the multiplicity of the singularities over here, which are called the pole locations, is only one. Multiplicity of these pole locations is only one. Now again, now we have simple poles, simple complex valued poles. Maybe we haven't seen this, but let me give it a try. Divided by s plus 6. Okay. Now I would like to find the partial fraction expansion of this thing. Okay. Now if I write this, how can I write that one? Well, would you agree that the first two terms, these two terms, will be coming up if I expand this? Okay. So I have an additional term, third term, plus 9 if I expand this fully. But I need a 25 over here. So I'm writing a 16. Okay. So right now this is equal to this. So now I see the following. This is, now what is the pole or the root of this polynomial? So if I equate this thing equal to 0, okay? If I equate this thing to 0, then how can I have the equality? So s should be equal to minus 3. If I put minus 3, I get 0 already, but I need to have minus 16 over here, isn't it, after taking the square? So I get rid of 3 by putting minus 3, and I put plus minus j4. So if I do that, well, you see I get minus 16 and so on. So I will call this, for example, this is minus 3 plus j4 minus 3 minus j4 as, let's say, pole 1. This is pole 2, something like that. Okay? Pole locations. So these are the values for which this is equal to 0. So this is s minus pole 1 then, plus s minus pole 2. There is a c over here. Okay? Now, how can I find a? Well, a is rather easy. You multiply both sides by s plus 6. You have a cancellation, and then you substitute instead of s minus 6. So I have 100 times minus 3 for this bracket. And for this one, I have, instead of s, I'm putting, let me see, minus 6, isn't it? 36 minus 36 divided by 25. So this becomes a is minus 12. Okay? That is it. So how about b? So for b, I multiply both sides by s minus p1. p1 is this. Okay, so if I write this one as S minus P1, S minus P2, this thing, okay, where P1, P2 one more time, there it is. I have the cancellation of this term and I should do the substitution. So how do I find B? 100, and so I have P1 plus 3. P1 plus 3 is J4, okay, and S plus divided by P1 plus 6. So P1 plus 3 was this. P1 plus 6 is, should be this. Okay, now I have, this is already cancelled because I'm trying to find B. I have P1 minus P2. P1 minus P2 is J8. Okay. So then this is J400. This is J8. So I have 50 divided by 3 plus J4. So let me write by its conjugate. So 9 plus this becomes 25. 50, 3 minus J4. So this becomes 2. You should be, as an electrical engineer, a future electrical engineer, somewhat, let's say, fast in these complex arithmetic, because this is our, basically bread and butter. Okay. So I have found this. So let me, in order to not to lose it, so this turns out to be minus 12. And if I am correct, this turns out to be 6, let me write it like that, minus J8. Okay. That is it. So let me check my results. 6 minus J8, which is this one. Okay. So how about C? So C, well, you do the same thing. Now instead of S, you cancel this one, and instead of S, you are writing P2. Okay. So this should be P2 plus 3. So let me write this. P2 plus 3. Okay. This is P2 plus 6. P2 plus 3 was this. Now, this is, which one is cancelled? P2 is cancelled. I have P2 minus P1. P2 minus P1 minus J8. Okay. I got that. So I can again do this calculation, but do you remember this? We have done a very similar calculation for B. So what is the difference? Well, if you check this, the difference is, instead of J, I'm writing minus J. Instead of J, I'm writing minus J, and so on. So if you do that, trivially, this is equal to B conjugate. I mean, you are replacing all J's by minus J. If you treat this like a symbolic variable, do the calculation and do the replacement later on if you wish. So at the very end, I should be getting B conjugate's equivalent expression 3 plus J4. Okay. Actually, this is always the case. This is always the case. So if you have a complex valued pole, so since P1, P2, they are complex conjugates of each other, as you see, or from here, as you see, P1, P2 are complex conjugates of each other. So you are calculating either P1 plus 3 or P2 plus 3, but they are complex conjugates. So similarly, you have the same situation over here. There is P1 minus P2, P2 minus P1, or maybe it's easier from this one. Whatever you do, you're always getting the complex conjugate of the earlier result. So essentially, once you have seen this, since P1, P2, they are complex conjugates of each other, and since in this left-hand side, only these coefficients are real valued, that is important, but in circuit theory, they will always be real valued. So if this coefficient is complex valued, clearly, if you take the conjugate of this result, then this would be, if this is like J3, it will be minus J3, and it will be, we don't have this kind of equality, okay? Because at the end, if you calculate the B and take the complex conjugate, you're also changing your f of s function at the beginning. But luckily, our f of s function is a function of s, but the coefficients are real valued, okay? That is the deal. So this is the end actually. Now, you can say that this is the partial fraction expansion. Well, this is the end. But let me go ahead one more step. Now, if this is f of s, my f of t is minus 12 e to the minus 16 ut plus 6 minus j8 e to the, let's say p1, sorry, let's put a bracket, e to the p1t ut, because pole location is at p1, plus 6 plus j8 e to the p2t ut. Okay, that is it. Okay, now how can I, process this a little bit more? So remember, p1 and p2 are like that. So maybe I should write what p1, p2 is. So let me write p1. p1 is minus 3 plus j4, and this is p1 conjugate. Okay, this is the conjugate of this. Okay, p2 is p1 conjugate. So how can I, deal this? So I would like to write these two terms over here one more time. 6 minus j8, okay, e to the p1t, e to the minus 3 plus j4t, and let me put this ut over here. Okay, and I have 6 plus j8 e to the minus 3 minus j this. So I have on the exponent the conjugate of this. So what should I do? Now I deal with this part. I write this as e to the minus 3 times e to the j4t, e to the minus 3t, e to the minus j4t, because it's the complex conjugate of the other one. They are still their complex conjugates. Okay. So how do I see this? As a function of time, there is a complex number evolving over here. There is another complex number evolving over here. For example, when t is equal to 0, 6 minus j8. For t is equal to 5, another complex number. But whatever complex number you have over here, its conjugate is next to it. So let's pull this e to the minus 3 term out, because it's the common term. Okay. So if I do that, e to the minus 3t, 6 minus j8, e to the j4t, 6 plus j8, e to the minus j4t, ut. Am I right? Well, one more time. If these are complex conjugates of each other, this box and this box, they are complex conjugates of each other. Then, why not write this as e to the minus 3 times 2 times the real part of only one box? Because if I add these two numbers which are complex conjugates, the imaginary part will be cancelling out. Okay? So 2 times is real part, it's the same. Imaginary part minus imaginary part, they cancelled. 2 times the real part of only this box or that box, doesn't matter. Now for this one, again let's remember Euler's formula. Again, as I have said, complex numbers are, you should be somewhat like fluent in these calculations. So I should calculate this complex number in product. Okay? So let's take this 2 out. 2 times, there's ut also over here, e to the minus 3t, and this box is 6 times cosine 4t, okay, minus j8 times j times sine 4t. So I have j square obviously over here. J square is minus 1, so this. and ut present like that. Okay. So then our final result is f of t. If we check this, f of t is, let's erase this part. Finally, f of t, this thing, minus 12 e to the 60 plus this thing, 2 e to the minus 3t, 6 cosine 40, 8 sine 40 ut. Okay, that is our final answer. And this, maybe I should be a little careful, this ut multiplies everything. Okay, ut is present at every term. Okay, so this is something. Now we have seen how to deal with complex valued poles. But I can also show you one more way of handling the same thing. Let's see. So what was this function? 100 s plus 3 s plus 6 and I have s square plus, or let me write it like this, s plus 3 square plus 16. Am I right? I had something like this. Okay. So you can also, because complex numbers are, I mean, it's convenient, it's not very difficult, but maybe for such simple cases, you can also do the following. Okay. So you can write here bs plus c. Of course, this b and this c is different from the earlier one right now. So if you wish, I can put a hat, b hat, c hat, not to cause any confusion. Now what is a hat? Again, the same operation. You multiply by s plus 6 and substitute s is equal to minus 6. So it should be this coefficient, isn't it? It should be the same. Minus 12. So previously we were using the residue method to calculate the coefficient of the other poles. They're again distinct poles, but complex valued. Now, how can I find b hat and c hat, you know, from here? Well, the observation is this. If you have such a simple case, why not this time equate the denominators this time? So I'm multiplying by s plus 6, and this thing will be multiplied by s plus 3 square plus 16. So the thing is that, of course, we would like to use the residue method, but if it is towards our advantage to use something else, if it is our advantage, why not use it? Okay. So, for example, what is the coefficient of s square on the numerator? 0. Okay. Now, what do we see? If I do this, so it's minus 12, s square is present if I do this operation. So I need plus 12 s square to cancel that. So then b hat, immediately I get it like plus 12. Okay, let me erase this. This is plus 12. Okay. So what else? For example, this coefficient, c coefficient. So how can I find that c coefficient? So to find the c coefficient, maybe I can look at the following. So I have 300 as the coefficient of s. Okay. So how about this? 16 times this. Oh no, this is 25, isn't it? This is 25 times this thing minus, but 25 times 12 is 25 times 4 is 100, so this is only the minus 300. So I need a 600 over here. So c should be 100 then. Okay, because this time c should be 600. Okay. So what do I have? Now I get the following. Minus 12 s plus 6 plus s plus 3 square plus 16. Okay. So 12, let me see, s plus 3 minus 3 plus 100. So what's going on? I have added and subtracted minus 3's over here. Then I will write this part as 12 s plus 3, s plus 3 square plus 16, minus, so this is 36 plus 100, I have 64, isn't it? Is it minus? It's, I think it's plus. 64 s plus 3 square plus 16. Let's check. This is minus 36 plus 100, I get 64. Okay, something like that. Okay, so if I take the inverse Laplace transform of this, so this term is when inverse Laplace transformed, let me write it over here, minus 12 e to the minus 60 ut. So what is the inverse Laplace transform of this? This is, you may recognize it, 12. So if you write a capital kind of S, $S value for this S plus 3, so this is like S divided by S squared plus 16. So with this dollar type of S, this is like cosine 40. Okay, cosine 40. But due to this, I don't have S, but this S plus 3 instead of that. So this will be, you can recognize it as e to the minus 3t cosine 40 ut. Okay, maybe you can compare with this. Okay, how about this one? So this one is something like that, but I should be a little bit careful. I'm writing 4 and 1 over 4. Obviously this is 1. So as you see, I have written s plus 3 minus 3 to create this s plus 3. Now I'm creating a 4 over here, and these two terms makes a 16. So then inverse Laplace of this is 16 times the inverse Laplace of this thing. But this has the inverse Laplace of this times sine. Where is my pen? Okay. So this is equal, this box is equal to 16. Okay. 16 times e to the minus 3t sine 40 ut, and you get this term also. Okay. So as you see, we have different methods. Important thing in engineering is that do not memorize a single method and do not use it all the time. Have alternative methods for a solution of even a simple problem like that. And use those alternatives cleverly. Whenever you need to do something, just think about how to do it. Do not memorize a single method. Maybe that is the most important message. Okay, now let's go ahead. This is still 1. Now, let's have let me see. Okay. Number 2. So repeated poles. Again, these examples are available in almost like every circuit theory textbook, but I just want to emphasize some things that probably you will be maybe not immediately observing. Okay. Now, again, how can I have partial fraction expansion for this one? Now you see that there are like s plus 1, s plus 1. There are two s plus 1 terms over here. So at least if you check the singularities, now singularity, singularity, and singularity. So that means that there is a double root over here of this polynomial present on the right hand side also. So how do you find A, B, and C? That is the partial fraction expansion. Well, how do you find A? Well, let's give it a try. If I multiply by S and do this cancellation, substitute in the final result S is equal to 0, I get a number over here, and this number is equal to A plus 0 times b after substitution, 0 times c, so I get a directly. So what's the value of that a? Do the cancellation, substitute s is equal to 0, a is equal to 2. Okay. So how about b? So if I multiply by s plus 1, do not memorize the method even. Well, you will see, just try to apply the method at least, using its proof. Let's see whether we will be running into difficulties. If I multiply by s plus 1, so this cancels only one of these terms. So this becomes 1. I cannot do the substitution. S is equal to minus 1 over here. I'm in trouble. So left hand side is not defined. So let's give it a try. If I multiply by s plus 1 squared. Okay. Now if I do the substitution, I perfectly cancel this term. So there is no pole at minus 1 right now. I can do the substitution. If I substitute s is equal to minus 1, this will be 0 times minus 1. 0 times a. So this would be b times s plus 1 after substitution. It will be equal to 0. And this cancellation. So I get the value of c. I couldn't get the value of b right now, but after s plus 1 square multiplication, if I substitute s is equal to minus 1, cancel this, substitute s is equal to minus 1. So this is 4. You have 6 minus 1 divided by minus 1. So you get 1 for this. Okay. So how can I find b? Well, if you have found so many things, like a and c, how can you find b? Well, you can do something like that. For example, what is the coefficient of s squared over here? 4. So if I multiply this thing by s plus 1 square, this thing by s times s plus 1, this thing by s, okay, I should be, if I'm focused on this coefficient 4, okay, so I get a s square, b s square, and cs, as you see. Am I right? So I get a plus b should be equal to 4. Okay. So from here I get b as 2 also. That's something like that. Now, what else? For example, can I check this term, 7, just for verification? So what is the constant? Well, coefficient of s over here, 2. I have 2a, 4 over here. What is this coefficient? It is 1. 4 plus 2, 6. Plus this one, 7. I get 7. Good news. I am happy. Okay? So this is one way of looking at it. Well, again, there is also a method by residue method. Well, I think you will like this method also. If this is f of s, okay. Now, residue method, let me put it in brackets, for repeated poles. Okay. Now, how do I do this? Well, only difficulty was finding b, as you see. B was giving us difficulty. So how can I do this? So here's another way of. So what is the idea of residue method? I have this equality, and if I have such an equality, I do operations on right hand and left hand side and try to kill all of these terms and leave maybe b alone. Okay. So how can I do that? So here's the idea: f of s times s plus 1 squared. Okay. Okay, let's give this a try. So for this one, so this becomes a s plus 1 squared s plus b s plus 1 plus c. Am I right? Well, let's remove this not to get confused. So I have multiplied this f of s by s plus 1 squared. Actually, at this point, how we get c is we substitute, after this product calculation, s is equal to minus 1, and clearly you see 0 plus 0 is equal to plus c is equal to this number. Okay. Now, how can I, get b, but I would like to null everything else. So here's the idea. take the derivative of this. If this is correct, this derivative should, with respect to s, if it's correct on a continuum, should also be correct. Okay. So again, you may think it like a trick, but again, this has some important results also. So how about this? You need to take the derivative of this product. Plus this, if you take derivative with respect to s, so you are taking derivative of this, and derivative of this one is equal to 0. So you see b is alone. But how about this? Well, you take the derivative and then substitute s is equal to -1. So this term will be equal to 0 when s is equal to -1. So how can I see this? Well, this is the derivative of a product. So this is first term, this is second term, derivative of this thing plus this thing times the derivative of whatever it is. You can see that because there are double poles over here, even if I take the derivative, this will be again 0 when s is equal to -1. Okay? If I don't take derivative and I substitute s is equal to -1, because of this double root over here at s is equal to -1, I get zeros. So this term will be 0 when evaluated. So then b is equal to, from here, I'm observing the following. You calculate this product and then substitute s is equal to -1. Okay. So again, this is the residue method. There is no equation solving like I was trying to find b by equation solving, but right now there is no equation solving. So let's give this a try. Okay. So b, residue method. So f of s times s plus 1 square. So then this is cancelled. DDS 4, 7, 2 divided by s. And then do this calculation and substitute s is equal to -1. But this part is, I think it's easy, 4s plus 7 plus 2 over s. Okay. Now its derivative is, with respect to s, 4 plus 0 minus 2 over s square, and then substitute s is equal to -1, so I get 2. b was 2, so we get the same result. Okay. So residue method, as you see when applied, it works. Again, if you have many terms, then you can single out this term with the application of this residue method for the repeated poles. So what else? This is number 2. So let's have a third one. Let's erase this. Number 3. Okay. So let me say proper slash improper fractions. So the question is the following: s squared divided by s squared plus 9s plus 20. So I would like to do partial fraction expansion. Do partial frac expansion of this. Okay. So how can I do this? Now you can say that, oh, okay, this is, let me see, this is s plus 4, s plus 5. Now we can say that rather easy. I have this thing, not repeated, real valued poles. Then a is equal to, let me see, this is minus 4, 16 divided by 1. B is equal to, cancel this, 25 divided by minus 1. That is it. Okay. So this is equal to 16. Let's erase this. This is equal to minus 25. Do you think this is correct? Well, don't be that fast. This is terribly wrong. Why it is terribly wrong? Well, if you equate the denominators, then on the numerator, can you have an s square? That is the deal. Okay? You cannot have an s square because you see that s plus 5, s plus 4 is needed to equate these denominators. Then first order, never have a second order. Okay. So where is the mistake? So of course I'm getting some values for a and b if I do this substitution. So where is the mistake? So the mistake is at the very beginning. So we have said that I have this equality. Okay, that equality, let me write it, is not possible. Okay, we don't have equality. A and b, if you select a and b as scalars, you can never have equality. Okay, so in other words, for example, look at the limit case when s goes to infinity. So on the left side you have 1, on the right side you have 0. Okay, if a and b are just scalars. So just be careful. So at the beginning we have assumed that there is an equality, and then we have done this calculation, okay, finding a and b. If there is equality, I can cancel this, then single out the other one. But if there is no equality at the beginning, I mean, your first step is wrong. So how can I do this? Well, don't do this, first of all. Well, let me write. Proper fraction if the degree, let me write not a sentence, but I think it's very simple. If the degree of the ratio, degree of the numerator is smaller than degree of the denominator, okay, this is called a proper, this is a very simple definition, a proper fraction, okay? Otherwise, improper. Otherwise, improper. For example, degree of the numerator is 2, degree of the denominator is 2, this is improper. So, before the application of residue method, check if the ratio is proper or not. Okay, this is very important, otherwise you will be making this mistake. So if it is not proper, if it is improper, now what can you do? So actually you should do the following, s square, isn't it? You just divide this. So do you agree? So what is this? S squared minus 9s minus 20. So the main idea, the division. If you divide this thing by this, there is this quotient, whatever you have, and there is this what we call remainder. So remainder is always a smaller degree than this divisor. Okay, that is the main idea. You just divide it. So quotient is 1. Or let's now check. Now if the limit s goes to infinity, I have 1, it's nice. So how about this one? This already proper. Okay, so write s plus 4, s plus 5 for this, and then you have 1, s plus 4, s plus 5. So for insert minus 4 over here. So I have 36, 16, okay. Insert minus 5 over here, 25 and minus 25, like this. Okay. So let's give it a check. For example, if I, let's look at the constant term. If I do this calculation, I have 80, I have minus 100, minus 20, so plus 20. So indeed the constant term goes away. Okay, so we are done. I'm always checking my results, because in case I make a simple mistake, I can recover from that mistake as soon as possible. Okay, so we have learned, this is very important as you see, to check whether the ratio that we are interested in is proper or not. So number 4 and the last thing. Number 4. So what was this? Okay. So this is about importance of u of t in inverse Laplace calculations. This is not about partial fraction expansion that much, but it is related, you will see. So let me see. 1 over s squared plus 9s plus 20. Again, this is continuation of earlier example. Something like this. And you can see that this is equal to plus s plus 5. Okay. Very easy to verify this. This is as simple as it gets. Now, if I take the inverse Laplace of this, okay, now let me call this f of s. Now my f of t is, okay, so this is e to the minus 4t minus e to the minus 5t ut. Okay, that is it. That is the Laplace transform pair. So how about this? We are done. So f of s is equal to s divided by s squared plus 9s plus 20. Now I have placed an s over here. Okay. So only difference is that there is an s on the numerator. So what does that bring? So you do this cancellation, but there is an additional term over here, s. So in this one, this should be, you can check this, this should be bringing a minus 4 over here, isn't it? Well, we can calculate it if you wish. This is s plus 4, s plus 5. But if this is 1, if I have an additional term s on the numerator, after this procedure, this is again another strength of residue method, I know that I'll be cancelling this s plus 4, but this time I have to multiply by this additional term. When substituted by minus 4, that will be giving minus 4 times whatever value this is. So I don't need to calculate it. So this one will be giving me 5 times s plus 5. So how about this? Now let me call this, not g then. G, this is something different. G of t. So what is g of t? Minus 4 e to the minus 4t plus 5 e to the minus 5t ut. Okay. Do you agree? Well, do you remember multiplication by s? So this is simply the first thing multiplied by s. But multiplication by s results in, you can say, differentiation in time. Indeed, if you take the derivative of this, derivative of that, everything matches. Very happy. Okay. Okay, so let's give it another try. So let me say this is h of s. So as you can make s, this is s squared this time. S plus 4, s plus 5. Okay. So how should I do this? Well, I have learned the trick. Now I have one more s term. So this should be 16. S plus 4, isn't it? Because I'll be substituting by, I need to multiply this thing by minus 4. Actually, you see how this derivative property works, as you see. So every time you differentiate, you are multiplying by this, either -4, -4, -5, and that also comes up over here, minus this. Okay. I have this thing. So this is the end. Do you think this is correct? Well, this should be correct. If this is correct, now this is the derivative of this one. It should be also correct, isn't it? Let's see. Indeed 16, indeed -25. It is correct. But let's be careful. Well, let's check this. I have said that this was wrong a few seconds ago. What was wrong? This was wrong. This was wrong. This thing. Because as you see, right now this becomes an improper ratio. So what is going missing over here? I couldn't have written this. So what's going? Something has gone wrong. So what is happening over here? So if you check this now, if you take, let's say, the derivative of this, so you see there's a mistake over here. So let's try to clarify this. I'm also erasing this. Now, how do you take the derivative of this g then? So what has gone wrong? Okay, derivative of this g. So derivative of this g dot is, so let me call this the first one, f1 of t. This is f2 of t. So this is f1 dot times f2 dot plus f1 of t times f2 of t. We should take the derivative that way. So this is my comment actually. Importance of having u of t in our Laplace calculations. If some students, or sometimes we don't write this u of t because we think that this answer is always valid for t greater than 0, and that u of t only signifies that. But from this, equality viewpoint, or from the algebraic viewpoint, this is the product of two functions, as you see. Okay. Now, if I take the derivative, if you use this derivative property, now what do you get? So you get this derivative of this thing, 16 e to the minus 40 plus minus 25 e to the minus 5t. This f2 is ut. Let me use another one. Ut plus f1 of t okay, this thing times, well, derivative of this thing is delta t. Okay. Derivative of that one is, as you see, delta t. Do you remember we have discussed this one? Okay. So what is this? This one is, if you check this, you need to evaluate this function. Let me call this f3. Well, this is actually f1. This is equal to f10 times delta t, isn't it? Because this is the product of a function by a Dirac delta. So this is Dirac delta again, scaled by the value of the function at the Dirac delta location. Okay. So that is it. So at the end, we get the following. This term also becomes delta of t. Now, if you take the Laplace transform of this, you get this term, you get this term, and you get, delta t also present as 1 in the Laplace transform relation. Okay. So again, in this calculation, we have made previously an error in treating an improper ratio as a proper ratio, and we end up with a let's say, mistake, and the differentiation property didn't work. But if you take the derivative carefully using this product rule of two functions, we see that everything is again, one more time, consistent. So what do I mean by that? Well, if this thing differentiated this way, okay, now this should have a Laplace transform of g prime of t, okay, which is equal to s times g of s minus g prime 0 minus, isn't it? And g of s was over here, so if you multiply it by it, s square, and g prime 0 minus is always equal to 0 because of this u of t. Again, because of this u of t, be careful. So we see that s times g of s corresponds to this. It's in time domain, it corresponds to this. And we have the same result. So, in conclusion, be careful with this u of t functions. Sometimes if you forget u of t in these calculations, you may get inconsistent results, like you see over here. So why did we get a consistent result over here? If I differentiate, we didn't see this. Well, if you differentiate, f1 becomes f1, this term becomes, when differentiated, it becomes this bracket. So ut is present. Now this is constant, this becomes delta t. But since this is already equal to 0, when t is equal to 0, this term does not appear over here. That was the issue, okay? That was the issue, and that was simplifying this calculation. So over here, this term at t is equal to 0, it was 1, as you see. f1, 0, this term is equal to 1. And that was creating the problem. So it's all related with improper, proper ratios, and so on. Because if you multiply by s all the time, you are differentiating the time domain function. So if you are differentiating the time domain function, do not forget u of t, otherwise your Laplace domain results and time domain results will not be, they won't be equivalent. Okay, that's all for now. We will continue with more discussions.